Twala, Shafiri Gunjani. I go by the name of Motizo. Welcome back to my YouTube channel. So today, katlekatle tlo ringa ka rengase ya fluid mechanics, the language that we'll be using Harituna fluid mechanics. So we tlo dilana pele le the SI units. So SI units are the international system of units. So they are the most widely system of measurement that is used globally. So hobaneng re hloka hore re frustane ka di SI units to standardize. Yes. So the SI units are made up of base quantities. Base quantities. So base quantities are fundamental quantities of measurement, such as mass, length, time, current, temperature, amount of substance, and luminous intensity. So don't be afraid kama asilungu that looks bizarre or tough. Luminous intensity. This luminous intensity is just the intensity of light. So from the other literatures, bazotshela is a photometric value of expressing the capacity, wara. So basically, this luminous intensity is the intensity of light from the light source. So it measures illumination. That's on its simplest form. So that's luminous intensity. But in our case, in fluids mechanics, we're going to deal with three fundamental quantities or base quantities, which are mass, length, and time. All of these base quantities, they have their base units. You understand? So the base unit of mass would be kilogram. The base unit of length is going to be in meters. The base unit of time is going to be in seconds. So I usually call it MLT. So so after dealing with the SI units, we're going to deal with dimensional analysis. So mass, it's a base quantity, base unit I think kilogram, length, base in meters, time, base in second. So current base unit is amperes, temperature is in Kelvin, amount of substance is mole. I don't know, chemistry, there was this topic, mole concept. That is the amount of substances. And luminous intensity, base unit candela, when you're dealing with mostly lighting, or either lighting your workshop or lighting theater, whatever you want to light. So how measure the intensity of light? You use the unit candela. So that's it. So from this SI units, we're going to deal with dimensional analysis. So dimensional analysis is when you have a natural phenomenon, you basically have a mathematical model that explains that phenomenon. Sure. So if you find an equation having several variables that you can solve, you basically chop it down to your base quantities, the mass, the length, and the time. So to eliminate or to find an equation that governs that natural phenomenon. So when you're going forward, we're going to deal with more of dimensional analysis, but this is just basic, Jeffrostan. So this is just the basic of dimensional analysis that we'll be dealing with. But moving forward, there will be a lesson about dimensional analysis, the Raleigh method, the Buckingham method. There are so many methods of dimensional analysis. So yeah. So from here, we will move to dimensional analysis. So dimensional analysis, like I just indicated earlier. So this, how a natural phenomenon, basically you're going to have a mathematical model that defines that natural phenomenon. But if you can't find an equation that or a mathematical model that governs that natural phenomenon, an equation that governs that natural phenomenon, you're going to chop the variables into to small base quantities, which is the MLT. The MLT is the mass, the length, and the time, the base quantities. First time. Sure. So this are the things. So dimensional analysis is built up of physical quantities. These physical quantities, key physical quantities have two portions. We have the primary physical quantities, which are made up of the base quantities. These ones that we just indicated when we're dealing with the ISI units, the Tomada. So, and then we have the secondary base quantities. So the best secondary base quantities are derived from the base quantities. So stuff like acceleration, power, pressure, force, energy, whatever the case may be. So those would be your secondary physical quantities because they are derived from the base quantities, which are these ones, which are the fundamental ones, the MLT. Sure? Well, so let's move on forward. So teaching a few examples to at least broaden your understanding ka fundamental dimensional analysis. So jwalo ka re tjhulo earlier, the fundamental base quantities that we're going to deal with hari ringa ka fluid mechanics would be the mass, which is measured in kgs, which is denoted hari tjhuna di dimensional analysis by the capital M. The length, which is base measurement is in meters, is denoted by L. And time, which is measured in seconds, is denoted by T. Sure. So acceleration is mass per second squared. So distance is indicated, is measured by length, which is in meters. Hence why we have our L here. And then time is measured in seconds, and it's T squared. So hence why the equation of, or the base unit of acceleration, or the unit of acceleration, is mass per second squared. Sure. And this equation, how we jonga kahle kahle, it's going to give you either we bhala kanje, or you're going to write it as L T minus 2 indices, the basics indices. So this is how we the basic MLT, the fundamental base quantities, how I deal with dimensional analysis. Let's move on to a little bit trickier example. So here, power. So power is work over time. Yeah? So work is force by distance. So I'm just chopping it down. So how do you eat an elephant? In small chunks. So kata so that it becomes easier. So work done is force multiplied by distance. Sure? So force mass by acceleration. So these are the basics. These are the things that you're supposed to know. They are the prerequisite. So they are the things that not what the first don't know. So force mass by acceleration. Yeah. And then distance is d divided by time, which is denoted by seconds. So hurry out to our fundamental base quantities. M is mass, is denoted by a bigger m in brackets, which is this one. Acceleration is mass by second squared. So sorry, it's meters per second squared. So meters of this distance, this one, and then the meters of acceleration will give us L squared, which is this one, this L squared. And then remember, acceleration is meters per second squared. So this second squared goes to the denominator times this second is going to be T cubed, which gives us the unit of what? Ne? This is just the breakdown of dimensional analysis using the fundamental base quantities. So the same is true with pressure. So our first standard of pressure is force over area. Force is mass by acceleration. So mass is denoted by a big M, and acceleration is meters per second squared, which is L over T squared, this L, and then this T squared. And then area is L squared. So when you divide those, you're going to get the unit of pascals, which is kg per second squared meters, which is Pascal. So this pressure, if ufuna uyituna using the pressure in fluids, it's still going to give you the same Pascal or the same unit. It's supposed to do that. So pressure in fluids is density multiplied by gravitational acceleration multiplied by height. So density is mass over volume. Sure, mass over volume. And then the gravitational acceleration is meters, which is the distance per second squared, which is time squared. And then the height is the length. So mass is denoted by M in, volume is L cubed, this one. The distance, this distance is denoted by this L. And then this T squared is denoted by this T. And all of this is gravitational acceleration. And this one is the density. And then this L is the height. So we broke down to the basic fundamental base quantities. So from there, we divide them all, and then we get to the same unit as the one that we did earlier, as Pascal. This one and this one are the same. So they are supposed to give you the same unit because they're both pressures. And that is it for this lesson. If you got a pansula, please subscribe and like the channel. Ola 7, I'm out.